Hello, on Answer Everywhere. It's almost Halloween, and we're reading some source code. I figured there's nothing spookier or more horrifying than a reminder that we live in an impersonal universe, that we're just floating around like little monkey specks. And so I thought it would be good to learn a little bit about astrophysics and cosmology. So I found this repo. It's called Swift. Swift. SPH. I don't know what SPH is. With fine-grained interdependent tasking. I don't know what any of that means. But it's about cosmology. They have a paper on their website that was useful, but I think Firefox crashed. So I don't have it up anymore. But let's pull that up. That's the code. We'll go to Swift Sim. And then somewhere, I guess under ADS. All right, so they have this paper that describes what they're up to. The paper is positioned as if the novelty, it's positioned for a physics audience. So the novelty is that they've cooked up some parallelism and some asynchronous programming. From our perspective, that's not so novel. We see that every single day. There is, I guess, a Swiss Googler here. And so from our perspective, the interesting part are the physics models. How do they work? What are they up to? And that's how we're going to look at it. And can I not scroll to the next page on events? What kind of world do we live in? So you see some equations here. I was hoping that I would have the best of all worlds, that I could scroll through everything and also have it be dark. But we see whatever this is, we have some integrator and then some force stuff. Ghosts are here. That's suitably spooky for Halloween. There's some sort of density, and then there's a sorting. Task hierarchy for the SPH computations in Swift, including communication tasks. Arrows indicate dependencies, i.e. an arrow from task A to task B indicates that task A depends on task B. Yeah? The task color corresponds to the cell or cells it operates on. And then I guess it's not explaining what ghosts are, but maybe like ghost particles. Ghost tasks. Ghost tasks are used to ensure that all density computations on a cell of particles have completed before the force evaluation tasks. Once all the force tasks on a cell of particles have completed, the integrator tasks, inverted triangles, update the particle positions and velocities. Okay, so they have a specific way for how to divvy this up for computation. And so on and so forth. So that's a useful thing to look at. It would be more useful if I could scroll between pages and not have it destroy my eyes with brightness, but that is what it is. So let's take a look at the code. We see tests here. I feel like tests are going to be crucially important for something like scientific computation. You want to make sure that you implement things correctly. This is all in C, I believe. Although the tests have some YAML, some text files, and some Python. But it would be nice if, it seems like you probably want the tests to be close to the code so you can jump between them and so that you can more easily add tests as you modify the code. But here's one test for test gravity derivatives. We have some standard headers. These are indeed standard headers. We're including Swift, which is the name of the physics thing that we're using, not the Swift language. And we have this thing, double D000. And this, I guess, brief is some indication that this is like a brief comment. This is presumably going to render in math mode. Maybe that's what /F$ means. We have phi is going to take Rx, Ry, and Rz. And Rx is the x coordinate of the distance vector. Y is the y coordinate of the distance vector. YR, I don't know. Are we in like spherical coordinates? And Rnv is the inverse of the norm of the distance vector. It's the norm of r, the -1. And whatever d000 is, we're just going to return Rnv, which we take as the last parameter. Why? I don't know. And then we have first order derivatives. And this is basically the same thing, right? Oh, no, we have an implementation. We're going to take negative Rx multiplied by Rnv, the cube of Rnv. Okay. So the thing that we're differentiating, maybe 1 here indicates what? This is like an indicator for x. Okay, so these are 0th order derivatives. This is like the first derivative in the first variable x. I'm going to guess that this is the first derivative in y. And the derivative is we're going to take the inverse of the length. This does seem to be like pretty spherical. And we're just going to divide the negative. Or rather, yeah, we're going to divide the negative by like the norm of the vector. Okay, so that's some test. Let's look at some actual code. And we also have examples. Examples might be the more informative place for scrubs like me who don't know anything about cosmology. Already, this is like by far the coolest folder I think we've opened up. We have black holes. Chemistry is mildly cool. Entropy floor sounds pretty cool. Cooling. I assume this is like the cooling of the universe. Obviously, we have to open up black holes. Well, I mean, we don't want to open up black holes. That's dangerous. But we can open up the black hole folder. We have gravity forcing. I'm going to guess this is like forcing terms on like an oscillator as opposed to something like set forcing, which I don't think that they use in physics as far as I know. We have hydro, probably something hydrodynamics. Light cone should be for the light cone of a space-time. MHD / none. Possibly what? Magnetic hydrodynamics. So like I think that's like the hydro meaning like fluids, that are dynamics meaning that are moving, and then magneto meaning that they have some magnetized particles or particles that interact with magnetic fields. That's possibly plasma related. I don't really know. Let's look that up. Magneto hydrodynamics. And when Firefox crashed, it took my LLM tabs with it. In physics and engineering, magnetohydrodynamics, MHD, is a model of electrically conducting fluids that treats all interpenetrating particle species together as a single continuous medium. I don't know what interpenetrating means, but somehow all of the different particle species, is this like the different kinds of particles, chemical species? Okay, so these are the different types of chemicals. We're going to treat them all together. And I guess primarily like look at how they interact with the magnetic fields or something. It is primarily concerned with the low frequency, large scale magnetic behavior in plasmas and liquid metals. It has applications in multiple fields, including space physics, geophysics, astrophysics, and engineering. Okay, so this is plasma related. I guess lightning is a plasma. Is lightning a plasma? I don't remember. Let's find out. Okay, so we'll add that to Wallabag to read it offline. All right, so I'll say think about all the things that people in magnetohydrodynamic study. Then draw the most intense and amazing picture of magnetohydrodynamics that you can use on a recruitment poster. I'll say the sky is the limit. That's nothing. Come on, Gemini. Make something cooler, much cooler. Okay. Well, whatever. Okay, we also have neutrinos. We have Riemann, presumably for Riemann surfaces. RT, I don't know. Russia Today, real time. Riemann tensor. I don't know what shadow swift is. I think I'm just going to skip it. We have to skip something. Star formation is probably cool. Stars is probably cool. Radiation transport. Thank you, Casper. Is this something you already knew off the top of your head, or did you look this up? Okay, radiation transport. That probably is somewhat interesting. Stars, tracers, and then we have a few files like headers and whatnot in the main folder, including the black holes header. In fact, these might just all be headers. They might have structured their includes so that the headers are in the main folder as opposed to like a separate include folder. So I think it's also often good to look at headers separately. But let's look at barrier. Might be like there's all sorts of things it could be. One thing it could be is like the barrier method for optimization. It could also be some sort of physical barrier. But let's look at black holes and IACT. Oh, Casper knows some of these terms because they're a physicist. Oh, okay. Well, I am not a physicist. I studied math, but I had basically no physics. So that's probably going to show through here. But I'm super glad to have you around if you know physics. We have cell black holes. I think cell is probably they described computation as taking place in cells. We also have cell grid. This is going to be stuff related to how they break up the computation, which is probably interesting for physicists who use this, but I'm not going to take an interest in it yet because I don't know the math stuff. And then we have cosmology header and the cosmology.c. I'm guessing that's probably an entry point. CSDS. I don't know what that is. Cycle might be a cycle in the. They're building a task graph, so presumably this is going to be a directed acyclic graph, and they're going to do some sort of topological sort to decide what order to execute the tasks. And cycles, I'm going to guess a cycle that is detecting cycles in the graph, but we'll take a quick look at that. Engine we'll ignore, and I think most of the rest of this we will ignore, although I'll look at the gravity header. And we see some other stuff like hash map. So this is kind of a mix of physics stuff and also data software stuff. Might as well look at the hydro header. Hydro space, inline, intrinsics, kernel hydro. Yeah, sure, we'll look at kernel hydro. We'll look at kernel gravity. And I'm going to look at these pretty quickly. I'm a bit under the weather, so I'm not, like going into this, I wasn't sure how long it would last. But so far, I'm feeling pretty good. Neutrino, parallel stuff, physics constants, sure, potential, power spectrum, pressure floor, etc., etc. Some rays, some runners, sync, space rebuild, space rebuild, and space recycle. I just think sound kind of funny. And then stars. Stars.h, stars.c. Statistics might be interesting. And then tasks. Okay. So it would be nicer if some of this were, the headers were organized a bit better. We have all the folders for a bunch of this stuff, but it seems like the headers are like a bit of a mixed bag with respect to what they're up to. So barrier, what was my theory here? That this might be optimization related. These are like thread barriers. That was not one of my theories. Define the thread barriers if the POSIX implementation on the system does not. Okay, so this is about threading. Black holes. Okay, so the header just has a bunch of a few includes. We're just kind of setting things up, and so I guess the real work is done in the folder. This is a Swift cell. This is going to be, I guess I just wanted to see if this was anything interesting. We've got a link. A link takes a task pointer and the next pointer, so it's a linked list. And gravity variables. The gravities, I'm a little bit surprised to see gravity variables in the cell, but not totally surprised. But they also have like star variables and maybe black hole variables. I don't know if these are all in cells or if like a cell can have some of these optionally. But it's basically stuff like that. I'm going to consider that bookkeeping. Here's cosmology. Cosmology has a current expansion factor of the universe. So this is, I think, already a little bit interesting. So as I understand it, which I would consider to be a very minimal understanding, that when you write down like the metric of a space-time, possibly with curvature, then it's common to have so at least in math, let's take a step back. So one of the things going on with relativity is that you have these metrics that where length isn't just like x squared plus y squared. We have this time dimension. Time has an opposite sign from the spatial dimensions. So in math, we think of time as having a negative dimension. So x squared, y squared, and negative t squared. I think in physics, they have the opposite convention, although I'm not positive. And then a, I think, is like is a factor that you can, I think maybe a is a function of time that is multiplying the spatial dimensions. But let's see if we can look that up. And Casper, you can tell me if that's way off. I'm not even sure what the right search term is. Expansion of the universe. This is the Hubble rate. What's the metric? Maybe like the something Walker metric? Somebody? Maybe the Friedman, Lemaitre, Robertson, Walker metric? Yeah, thank you. There you go. Yeah, I think this is right. So I think this is, I don't know what tau is, but I think negative c squared dt squared is the negative part of the metric. I'm not sure what c is. And then we have this a of t squared. And then we've got d of big sigma squared. And sigma is going to range over the three-dimensional space uniform curvature. C is the speed of light. All right. Well, there you go. So that's a common thing. I guess C is there to kind of normalize it so that all of your numbers don't have huge, as you're doing computations on the cosmological scale, you don't have numbers that have however many figures. 10 to the something or other. Yeah, I thought you guys worked with C equals 1. So 299,792,458 meters per second. You don't want those huge 9-digit numbers mucking up your computations. You're just trying to get through the day and compute things. And also, where did my GitHub things go? Here. Okay. All right. So that's what I think is going on with that A. And again, I don't understand this, so maybe Casper can tell me if this is true, but we have a certain regime in the universe with a certain expansion rate that is observable. And I think possibly as you like go back in time where before we can observe stuff, the expansion rate might change over time. And that's, I think, what it means by current expansion factor of the universe. This could mean current in the sense that like it's estimated and it's converging on a specific thing, or it can mean it's something that depends on kind of where you are on the manifold. And it's going to kind of crunch down to the black hole, the like Big Bang singularity or whatever. However it works. And then we have the inverse of the current expansion factor of the universe. This is A inverse. I guess A is a function. So this is, I don't know if this is 1 over the function or we're going to try to invert the function in the sense that we're, it says that the compositional inverse, A inverse composed with A, is 1, or if it means A times A inverse is 1. So in the basic model, says Casper, it's a function of cosmological time. It goes to 0 as time goes to 0, as we approach the Big Bang. Okay. So A, if I'm understanding correctly, so when you say it goes to 0, do you mean like absolute value of A, or the normal of A approaches 0 as t goes to 0? Something like that. So I guess it's not, yeah, I guess that would make sense if that's the correct interpretation. That would make sense why there's like that would be a contraction, right? If the expansion is smaller and smaller. Yeah. Okay. Cool. Thank you. This is, I'm so glad you're here. I really appreciate it. Okay. And then we have the inverse cube of the current expansion factor of the universe and so on. This is just some struct. Why is it including these? I guess it's just cheaper than computing them. The term scale factor is also common for data. Okay, cool. That's great. And then we have the power of the scale factor in A factor pressure, A factor sound speed, A factor mu. These are powers of the scale factors used for relative velocities in maybe viscous terms. I don't know. I guess maybe we're doing fluid stuff, so viscosity might show up. I think viscosity is something that's also studied in general in PDEs. But again, I also don't know about PDEs. Okay, so we're recording lots of stuff. We're also recording the Hubble constant at the current redshift and the critical density at the current redshift. So one thing that jumps out at me is that this is to buy into this, you have to buy into like general relativity, I guess. I don't know if there are like crazier models that people are working with that are like slightly different, that have like different parameters. But this is like I think this is the like by far the standard regime for how you study cosmology. Like I don't know I know that it's kind of unknown what happens like really close to the Big Bang. I think that's still something I believe we're trying to work out. I just don't know like all of the different ways of trying to think about modifying the equations in like quantum gravity or whatever comes up. All right, then we have expansion rates at the current redshift and all of this stuff. So this is cool. This is a struct that just has a bunch of variables. And this is just all the stuff they're keeping track of. And then this is the header. And this is kind of like a God struct in the sense that like all of the things I think that you could need are going to be in the struct, and we're probably just going to pass it around as sort of like a context. So cosmology update is going to take this cosmology struct, a pointer to the struct, and I guess a list of a struct of physical constants. This is possibly so that you can try different, maybe so that you can try different constants and see how they work. And then an integer time, which is the time current. And it's void. So I'm not sure what it's going to output. Maybe it will update the cosmology struct pointer. I see this thing, time at the present day, A equals 1. Universe age at present day. So maybe it updates things like the time as you march along, time between Big Bang and the first entry in the table. I'm guessing some of these might be out parameters that you get back an updated cosmology thing. And we also have other functions like get drift factor. It's kind of like a getter, I guess. It might do some computation or it might just pull out a field. Core kick factor. Core, maybe correlation Coriolis. How many R's are in Coriolis and how do you spell it? First of all, it's an I, not an E, and there's only one R. So I'm going to guess correlation. Delta time, get time base. Cosmology init, no Cosmo. I don't know what no Cosmo is. And then you can like pretty print, I guess, your cosmology stuff. And you can write the model. You can dump the struct and restore it. And then here's cosmology at C. Let's see how they return stuff. This thing is returning a table. Interp table. Let's look at cosmology update. Update the cosmological parameters to the current simulation time. So I just want to see if they're going to write to C. Yeah, Z old is going to be set to CZ, etc. So we're modifying C, and that's both an in parameter and an out parameter. And is it worth looking? Yeah, I guess we might as well look at the update routine. I don't remember what Z is, but it's like the previous state. So we're going to save that. A, I think, is the scaling parameter. And then we're going to get the scale factor and powers of it. C A begin times, we're going to exponentiate the current time times the C time base. That's going to give us A. And then A inverse is going to be the multiplicative inverse. We're going to divide by A. Z is redshift. Oh, cool. And then we'll set the new A to this thing that we got by exponentiating. That's a cheap, I think, it's just some exponentiation that doesn't seem to be anything especially fancy from a computational point of view. And then we're just keeping the inverse. I'm not sure why. It could be for computational simplicity. It could be because it may be nicer to have the inverse around than continuing to invert it because of numerical stability for some reason. And then we're going to compute these like square inverses and cube inverses. Doesn't seem like we're checking anything about whether they've like gone to zero or what have you. And then we're going to compute things like the A factor internal energy, which is we're going to raise A to the -3 power. We're going to raise A to the power of -3 times the hydro gamma -1. I'm not sure why. Okay. But we have A to the, isn't this already A to the -3? Why don't we use that? I don't know. Okay. So these are a bunch of computations. Gravity kick integrand computes dt over A for the current cosmology. So dt should be change in time, I guess, and A is a scalar, right? A is the scale factor of interest, and the current cosmology is a parameter. Okay. So let's move along. CSDS, they contain messages representing the particle data at a given point in time during the simulation. The CSDS messages always start with an 8-byte header, structured as follows. You have some mask and an offset. i.e., a first mask byte followed by 6 offset bytes. The mask contains information about what kind of data is packed after the header. The mask bits correspond to the following data. Okay, so they have some like binary protocol that they're sending messages about. Seems like they could probably mostly reuse other things, but who knows? Maybe they don't know about those things, or maybe there's a reason that needs to have a custom packing cycle. I think my theory here is that it's possibly a cycle in the task graph. Machine-dependent cycle counters code needs to be inline. To use the cycle counters in your code, simply include cycle.h. So I guess this is not about detecting cycles in a graph. I think this is about keeping track of how many CPU cycles you use, which we're going to ignore. Gravity, I'm going to guess, again, this is like a gravity struct, which it's not. We've got these functions like gravity exact force, ewald init, ewald evaluate. I'm not sure what that's about. We're going to move along from there. In fact, I think I'm going to move along from these headers in general and take a look at some of these folders. Now that we have a sense of what's in the headers. Okay, so should we go to examples or let's see. We have examples, cooling, black holes, eagle. I don't know what eagle is. Let's just check one of these headers at random. This is some inline function. Black holes compute time step. So this is probably the main time step computation. Computes the time step of a given black hole particle. So I guess of a single particle. BP is a pointer to the S particle data. Props are the properties of the black hole scheme. And constants are the physical constants in internal units. So we do what? We've got the speed of light, which is a constant from here. So that's C. You might set speed of light to 1. Hi, Kevin. How goes it? And then we compute the instantaneous energy supply rate to the BH energy reservoir. BH is presumably black hole. And this is proportional to the black hole mass accretion rate. So the energy rate with a capital E, which is a little bit unusual for a local variable. We're going to take the props, which is the cosmology struct that we saw. This like the God struct. Props has some epsilon r, and we're going to multiply it by an epsilon f that's also in there. BP has an accretion rate. BP came from where? It's passed in, I guess, is the first parameter. No, I was wrong. Props is black hole props. Okay, so these are all black hole properties. I don't think we've seen this struct. But black holes have epsilon r, epsilon f, and an accretion rate. And we're multiplying them by the square of the speed of light. That's energy rate. So energy should be equal to mc squared, if I know the nursery rhyme correctly. So I don't know if that means that this is the mass of the black hole in some sense, which is proportional to the black hole mass accretion rate. Something like that. Okay. If the energy rate is 0, we're going to return FLT max. B, if the black hole is not accreting, can't estimate their time step length based on the time scale for heating. Okay, then we have average particle mass in BH's kernel, etc., etc. We're going to compute the average time between heating events for the given accretion rate. This time is multiplied by the number of NGBs to heat, because if more particles are heated at once, the time between different AGN feedback events increases proportionally. Okay, so we're going to divide by the energy rate, and we've got E heat, which I think we computed here. We're going to multiply by whatever an NGB is. NGBS. I don't know. And then the new time step of the BH cannot be smaller than the minimum allowed time step. We're going to take the max of DT heat and props minimum time step and then return that. So I have two questions. One is, what is NGBS? And the other is, I'm going to ask the LLMs to tell me about that equation. National number of NGBs. I guess I don't care about forcing. Let's do a search for NGBs. Gigabytes per second. Gas neighbors. Total mass of the gas neighbors. Is G something related to gas? Total number of neighbors. Oh, NGB is neighbor, I guess. So I don't know if this is like neighbors in the like the particles neighbors or the black holes neighbors. Explain this line of code. Property blah 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 blah. This term accounts for the likely refers to the speed of light. This term accounts for the conversion of mass to energy via Einstein's famous equation equals mc squared. By multiplying by c squared, the mass accretion rate in units of mass over time is converted to an energy rate in units of energy over time. Okay, so I guess the mass accretion rate is mass over time, and we're converting to so the stuff there, which is what I was confused about, is not just mass, it's a mass rate, and that's why we get an energy rate. That all tracks. Oh, hello. Kavya Priya. Thank you. They say they're a big fan from India. I appreciate that. I'll say draw a image of, so write a battle rap about this line of code, and also draw a picture of the rapper circling, being sucked into a black hole. The epsilons are efficiencies, says Casper. The accretion rate is mass per second, so multiplying by speed of light squared gives an energy rate. Yes. Okay, thank you. I don't know what an efficiency is, but that makes sense. All right, so here's the guy being sucked into a black hole. Here's the battle rap. I'm not going to read it, but I'll scroll through it so you can read it at your leisure and pause as needed. Okay, great. I did enjoy that. Thank you. All right, so this is black. That's how they compute the black hole time step. This is some stuff for initializing the particle. So that's a header. I want to see, I think, some examples. Let's pull examples out. We have cosmology, cooling. I don't know what eagle is. I don't know what gear is. Eagle could be DM only snapshots of the Eagle suite of simulations. I don't know if this is something specific to this project, or if Eagle is like a general simulation thing. The Eagle simulation. Evolution and assembly of galaxies and their environments. It's a project to campaign of large-scale hydrodynamical simulations of lambda-cold dark matter universe, run by the Virgo Consortium. 6.8 billion particles, and required many months of computing on some of the world's largest supercomputers. Okay, so this is an existing simulation project. I'll add it. Wait, what? I'll add it to Wallabag so I can read about it later. And Gear, I'm going to guess, is another project. Physics? How about universe? How about cosmology? I don't want a simulation of I don't want like a picture of a gear rotating. There's like Quixote simulations. Let's look at Agora Cosmo. Initial conditions for the Agora simulation presented in Roca Fabrega et al. 2021. The initial conditions are generated by music. Pythagoras would approve. He's a big fan of the harmonious music created by the space, universe. And thus the path to the binary should be set in run.sh. The initial conditions are generated for a repo and then converted to Swift compatible IC with Python 3 script. Okay. So this is some other simulation. I don't know. You got get IC, music.conf. Let's look at music.conf. This is configuring some stuff like box length, level max, padding, overlap. I don't really know what any of these are. These are like cosmology things. Omega M, Omega L, H0 is maybe the Hubble thingamajiggy. And this is maybe configuring something about Poisson. Poisson what? I'm guessing this is part of like numerical solvers / optimizers because we have what I assume is fast Fourier transform fine. Yes, we want fine. We've got an accuracy, a grad order, presumably something about gradient, maybe doing some sort of gradient descent sort of optimization thing. But that doesn't tell me a lot about the universe. Will any of these tell me about the universe? How about cosmology? Co-moving shock, neutrino, cosmo. So we have so this is like configured with a YAML file, which is fundamentally just basically like JSON. So that's reasonably up to date. So here's a configuration for some neutrino cosmo thing. We've got we're configuring things like unit masses. This is the internal unit system. I guess these probably go into the struct that we didn't look at, but there was a struct for like physical constants. And I'm guessing these are the sorts of things that might go in the physical constants. And then we have the cosmology stuff. This is presumably the stuff that goes in the cosmology struct. H being the Hubble. What is it? The Hubble parameter. Edwin Hubble. The Hubble constant H0 is constant at any given moment in time. The Hubble parameter H, of which the Hubble constant is the current value, varies with time. So the term constant is sometimes thought of as somewhat a misnomer. Well, yeah, I guess literally it is a misnomer if it's not constant. Okay, so there's some, what do they call it? The variable? Parameter. So it's a parameter. Okay, the Hubble constant is most frequently quoted in kilometers per second per MPC. Parsec? Milliparsec? Megaparsec? Which is like a unit of how many... It's a unit of Kessel runs, if I understand correctly. So simplifying the units of the generalized form reveals that H0 specifies a frequency, leading to the reciprocal of H0 being known as the Hubble time. Okay, but anyway, it gives the speed of a galaxy 100 megaparsec away as 70 kilometers per second. So it's kind of like expansion, right? Is it the same as expansion? The Hubble constant relates the speed by which a distant object is moving away from us to its distance from us. Okay, so objects moving farther away might move at different speeds. But I feel like that would be computable from the expansion rate, but maybe that's not correct. It's the time derivative, okay, of the scale factor divided by the scale factor. Perfect. Thank you so much. Yeah, perfect. Okay, so it seems like you don't have to specify both of them. And so maybe you have the option of specifying either. So this is specifying H, and it's specifying A begin and A end. And I guess that gives you the evolution that gives you, I guess, like a differential equation to solve for A. And we've got N new and a bunch of other stuff. And we've got some time integration stuff that tells us essentially like how fine is our. We're essentially discretizing everything. It's a computer, so we're discretizing time. And I guess this is like the smallest discrete unit of time or something along those lines. And then it's configuring the scheduler and some snapshots. Presumably, like maybe how often to take snapshots. The base name is box, I guess, and whatever compression 4 means. And restarts after 4 delta hours. I'm not really sure what that means. And then we'll give it initial conditions as an HTF5 file, which is the same file format that like was used by Keras for like machine learning snapshots. This is some file format. Hierarchical data format. Designed to store and organize large amounts of data. Originally developed at the National Center for Supercomputing Applications. Okay, so this is some file format for saving things like snapshots and I guess also initial conditions. Then we've got some gravity configurations. I don't know what eta is. Mach is geometric. We are in some form of relativity, presumably special. What? Which one's the curvature one? Is that general? The one with curvature is presumably what we are in. Okay, so special relativity is objects moving at constant velocity relative to each other. Expands on general relativity expands on special relativity to include accelerated motion and gravity. It describes gravity as the curvature of spacetime caused by mass and energy. Okay, so presumably geometric might mean that gravity is given by the not the tensor, but the metric, the geometric metric, or something along those lines. I don't really know though. I don't know what Mach is. Okay, so that's configuration. And we have getic.sh. We're going to wget some this file from the, I guess the whoever these people are. And then we're going to just extract it and run it. And that's really all there is to it. The example itself isn't really here. It's hosted on that website. Okay, so let's plow along. Let's see if there's anything. I don't know how much longer I can go here, but Anarchy PU we have to look at. Okay, so this is hydro. This should be hydrodynamic stuff. Anarchy, I'm guessing that's like highly random. Whatchamacallit? Pressure, planetary. Look at planetary. Hydro parameters, hydro part, hydro.h. We'll take a quick look at hydro.h. We're going to include adiabatic index. Define planetary SPH, no Balsara, to disable the Balsara switch for the artificial viscosity and use the vanilla monogon instead. This is the funny thing to me about different fields. Like, every field has its own terminology. And it all sounds like gibberish if you if you don't know what they're talking about. There's just like, there's some Balsara switch, which probably makes a lot of sense if you know this field. And but if you don't, it's just kind of like saying random words. Okay, so returns the physical internal energy of a particle at the last time the particle was kicked. For implementations where the main thermodynamic variable is not internal energy, this function computes the internal energy from the thermodynamic variable and converts it to physical coordinates. Okay, so this is computing the physical internal energy from the hydro stuff. It takes in a part, an X part, and a cosmology, which is basically all of the information about the universe model. And we're just taking the X part, getting whatever U full is, and multiplying it by the A factor internal energy. And one of the really nice things about this this repo is that all of the implementations that we've seen look really small. So it's easy to kind of locally check that code is doing the right thing. It's a little bit harder to, I guess, globally check without a lot of tests. And to find the implementation of the real core of the implementation of a function might be a little bit hard because you might have to dig around for a bit. But I think this is probably pretty close to how a mathematician would chunk all of the information and think of like each local step as being relatively simple. And it's just learning what all the local steps mean is the kind of hard part. Here's light cones. We have an index. I'm guessing that's maybe to keep track of the light cones, whether to write extra log messages, which particle types we're doing. I don't know what the particle types are. We have minimum redshifts, maximum redshifts. Maximum A to search for light cone crossing for each type. A, I'm guessing, is still related to the scaling parameter. So I'm not really sure how light cones change with the scaling. I think the basic idea is that for like particles to interact, their light cones have to intersect. And so maybe the intersecting is governed by the scaling, which would make sense because the scaling shows up in the metric, and the metric governs the curvature. But I don't know, for example, how crazy a curvature you can get with that form of a metric. And so that's part of the reason I'm not really sure how to think about this stuff. We can check type for crossing, whether we need to do light cone crossing checks for each type at this step. I think A, since it's usually monotonically increasing anyway, is used as a type of time coordinate. Okay. So, all right. So A we're going to think of A as monotonically increasing. So A as a function of time always has yeah. Okay. Thank you. Always has like a positive derivative. So you integrate from one scale factor to another, not from one. Oh, okay. Okay. I see. That makes sense. So that's and then okay, so we're thinking of A as kind of like time. What is so? I don't know what proper time is, but I think that's different, right? Any frame here assumed to be time lag between two events is expressed as this. This looks like a metric. We've got this. What is that? Nu sub mu eta. It separates points in the trajectory of a particle. Think clock. The same interval can be expressed in coordinates such that at each moment the particle is at rest. Such a frame is called an instantaneous rest frame. The proper time interval is defined as the delta tau is we're going to integrate over p d tau, integrate over p ds over c. I'm not sure. First of all, I don't know where tau came from. Is tau time? T is time. Somehow we got a tau. I don't know. All right. Whatever. We'll look at that later. Okay, so we can enable selective output through of high redshift gas. Proper time is the time experienced by an observer moving along a geodesic. Okay. Because of time delay, so this might be different from the cosmological time. Okay, got it. So, yeah, okay. That makes sense. Thank you, Casper. All right, so we've got a bunch of stuff. These are all light cone properties. And we've got things like min Z for gas filtering. Z is what, redshift? I don't know what gas filtering is, but these are all things that I guess light cones care about. We have an output subdirectory. So this is a little bit of a mix again of physics stuff and also computery stuff. I'm guessing that maybe one of the reasons they have like an output directory is because there are a lot of light cones, possibly one per particle. Certainly, every small enough. I'm guessing that every small enough subdivision of space, you might need to model the light cone. So there's presumably so many of these that you can't store them all in memory, and I'm guessing that's part of the reason that you store them on disk, and that each light code might want to know where it's stored. And then we have range and expansion factor covered by particle outputs and helpix maps. And some buffer chunk size. This looks more like memory stuff, some gzips, box size. List of periodic replications to check on this time step. I don't know what we're replicating. Maybe we're doing the same computations multiple times or something along those lines, or maybe some other meaning of replication. And then we have light cone init. It's going to initialize a bunch of light cones. We pass it a bunch of things like properties, index, the cosmology struct, some params. You can clean the light cones. I'm guessing that's probably mostly about the data side of light cones and not the physics side. You can restore them, buffer, etc. All right. This is magnetohydrodynamics. I have a feeling like I have a pretty good sense of the code. I don't have a good sense of the physics, but Casper, you being here has helped me out a great deal, I feel like. All right, so calculate the neutrino. This is what? Fermi-Dirac in neutrino. We're going to calculate the neutrino density at the particle's location in phase space. So now we're working in phase space according to the 0th order background model. F sub 0 of xpt. So P, I think in physics is momentum. X, I'm going to guess, is position. I don't know if it's a vector in time. And we have the Z is the argument of the FD function. But Fermi-Dirac. Return the microscopic neutrino mass in EV based on the particle seed. Is Fermi-Dirac an equation or a statistics? Is it integral? And also statistics and a distribution. I don't know which one we're doing here. Let's look at the complete one. In mathematics, the complete Fermi-Dirac integral, named after Enrico Fermi and Paul Dirac, for an index j, is defined by f sub j of x is 1 over the gamma function of j plus 1 times the improper integral from 0 to infinity of t to the j over e to the t minus x plus 1 for j bigger than negative 1. And it equals the negative of the Pauli logarithm at j plus 1 of negative e to the x. And the Pauli logarithm, I guess, is the thing that has a series formation. We're going to sum from k equals 1 to infinity of z to the k over k to the s. I'm guessing z is a complex number. What is s? S is the subscript here. Oh, okay. The integral appears when integrating the distribution. I think, okay. It might be both. You might need it as a normalizer. Got it. Thank you. So this is the integral? Gamma is basically the, what's it called? Just the gamma function. What's the thing called when you multiply a thing by itself? N times n minus 1 times n minus 2. Factorial. Yeah. So gamma is basically the factorial. And so this, we're essentially dividing by the factorial of j plus 1. J is an integer, right? So is this ever not a factorial? I guess j ranges from -1. So we get like a gamma of -2 and a gamma of -1 and gamma of 0 maybe. But other than that, these are just exponentials or factorials. And then this is just some integral of the integration variable over this exponential thing plus 1. Okay. And then Fermi-Dirac statistics is a type of quantum statistics that applies to the physics of a system consisting of many non-interacting, I guess maybe neutrinos, since they're neutral or non-interacting identical particles that obey the Pauli exclusion principle. Factorial, yes, thank you. J is 1 minus the number of spatial. Okay. It's 1 minus the spatial dimension. So J is constant, it sounds like, and is negative. So if we're in three space dimensions, then it's -2, which it makes sense why we need the gamma, not just a factorial. That interacts via the weak interaction and gravity. It's electrically neutral and its rest mass is so small that it was long thought to be 0. Okay. I'm going to just guess that we're using Fermi-Dirac because with neutrinos because they don't interact much, but I'm not. Oh, number of dimensions -1. Okay, so it's 2, which would be easier to compute. Okay, so that's the Fermi-Dirac density. We've got some optimized XF. I don't know what F means, but I'm guessing that it's an exponential function. Z is a float and not a complex number. And then we've got this thing, neutrino C to mass. Return a microscopic neutrino mass in electron volts, I think is probably what EV means, based on the particle seed. We simply cycle through the masses defined in the cosmology. And so on. Return the particle mass degeneracy based on the particle seed. Cool. This is all very cool. I don't know what a neutrino header is, but maybe it's going to tell me something cool. We've got this this m zeta 3 is some number. Oh, it's the Riemann function zeta of 3. Let's see if the internet knows about this. XPF is for floats. Oh, yeah, good point. So this has the sequence 1, 2, 0, 2, 0, 5. Can we spot check this in any way? I guess not. 69031. Let's check that. 69031. This seems to be the sequence. Apéry's number, constant zeta of 3, decimal expansion. Yep. Looks good. And we've got comments. A natural question is whether zeta of 3 is a rational multiple of pi cubed. This is not known, though in 1978, R. Apéry succeeded in proving that zeta 3 is irrational. I love stuff like that. This it's harder than it might seem. Okay, this is from what year? I don't know, but it's from Stan Wagon, I guess. It's kind of wild. I guess I'll read this. All right, I'm going to ask the ChatGPT whether it knows what this number is. Tell me everything you know about. Okay, and there's the constant, is the value of zeta of 3. Cool. All right. What else? We've got a neutrino model, which has this car, which I'm guessing is probably used as a Boolean, use delta F mesh only. And you have M nu EV and deg nu. These are doubles. I don't know what they do. And N is maybe the number of neutrinos fac. I don't know, but some mass floor and a neutrino seed. I don't know what the neutrino seed is doing. Possibly there's like a randomness to the modeling of neutrinos. Apéri's constant occurs when integrating the Bose-Einstein distribution. I'm not sure if it occurs as well with the Fermi-Dirac distribution. Cool. Bose, where's Bose? I just want the article on Bose. So the Bose-Einstein story is a cool story. And there was a guy, there's like, who was here? Somebody was here from India. Kavya Priya. So I figure we should give Bose at least a little bit of love since he's showing up. So Satyendra Nath, maybe? Bose was an Indian theoretical physicist and mathematician. He is best known for his work on quantum mechanics in the early 1920s in developing the foundation for Bose-Einstein statistics and the theory of Bose-Einstein condensate. A fellow of the Royal Society, he was awarded India's second highest civilian award, the Padma Vibhushan, by the government of India. The class of particles that obey Bose statistics, bosons, was named after Bose by Paul Dirac. A polymath, he had a wide range of interests in varied fields, including physics, mathematics, chemistry, biology, mineralogy, philosophy, arts, literature, and music. And he was born in Calcutta. And I'll read more about him later. I'll add him to Wallabag, his Wikipedia page, that is. Not literally him. This is Riemann. There's actually not much here. We have Riemann vacuum. This is presumably like Riemann surfaces. Check if the given input states are vacuum and will generate vacuum. I'm not sure how they're modeling it. A vacuum Riemann solver based on section 4.6 in Toro. I don't know what Toro is. Riemann solvers and numerical methods for fluid dynamics. Okay, so there's some book here that has some guides for like practicing mathematicians about whatever a Riemann solver is. Presumably it's going to solve some stuff maybe over a Riemann surface or something similar. A Riemann solver is a numerical method used to solve a Riemann problem. Oh, it's a Riemann problem. They are used heavily in computational fluid dynamics. Riemann solvers are specific methods for computing numerical flux across the discontinuity on a Riemann problem. I don't really know what a Riemann problem is, but it seems to be differential or PDE related. It's a specific initial value problem composed of conservation equation together with a piecewise constant initial data, which has a single discontinuity in the domain of interest. Okay, so there's a discontinuity. I think that's unusual among like classic PDEs or differential equations. The Riemann problem is very useful for understanding equations like the Euler conservation equations, because all properties such as shocks and rarefaction waves appear as characteristics in the solution. And it doesn't appear to be related to Riemann surfaces in any way. Okay, so this is like a differential equation solver. I didn't see the equation, so I'm not sure if there are partial derivatives or not, but it's a thing. RT was what? Radiation transport? Radiation transport. And we see the gear stuff. I don't know what none is. And I'm not, well, I guess we'll look at the struct quickly. Oh, for no radiative transfer struct. Radiative transfer. It's the physical phenomenon. Why is it always zoomed in? Oh, no, it's because I'm zooming, trying to make the font smaller, I think. Of energy transfer in the form of electromagnetic radiation. The propagation of radiation through a medium is affected by absorption, emission, scattering process. The equation of radiative transfer describes these interactions mathematically. Okay, there's a spectral radiance in radiometric terms. I don't know any of these words. Spectral, presumably relating to the spectrum. What spectrum? Maybe electromagnetic spectrum, maybe eigenvalue spectrum. I'm guessing electromagnetic spectrum. And I'm going to stop soon. But this is interesting. I know even less about radiation stuff than I know about anything else. QLA, I don't know what that could be, but let's look at star formation. Star formation model used in the Eagle model. So there was also an Eagle folder. This seems to be a different folder. We have a critical overdensity. I don't know if that's overdensity of the gas that becomes a star. Calculate if the gas has the potential of becoming a star. Perform the star formation law properties to use. Or star form. Okay. So we have a bunch of gas. And this function will calculate. It's inline. Is this this is just the header file. It's going to take cosmology, whatever these part stuff is, XP the additional properties of the gas particles. Okay, so part is particles. So P are the gas particles. XP is additional properties of the gas particles in some physical constants, the cosmological struct, properties of the hydro scheme, the units, and cooling data. And the last thing it takes is the entropy floor assumed in this run. And it's going to do some computation. Whatever the model is, we'll see if these gas becomes a star. And then what if it does become a star? I don't know. Something has to change. And here's some star stuff. Stars debug, stars.h. You can compute the age of a star, and so on and so forth. And I think we'll just quickly look at these last two. That's radiation transport and anarchy. I'm just mildly curious what they're describing as anarchy. Anarchy pu/hydro.h, pu conservative implementation of SPH with added anarchy physics. : thermal diffusion. The implementation corresponds to the one presented at the Swift documentation in Hopkins, a general class of Lagrangian smooth particle hydrodynamics methods and implications with fluid mixing problems. I hope that anarchy physics is a general thing. Anarchy in physics can refer to a few different things. Neutrino anarchy, a phenomenon in which the neutrino flavor structure appears anarchic, which can challenge flavor models. For example, one study found that minimal extensions to the standard model can reconcile the neutrino anarchy with hierarchies observed in the charged fermion sector. Anarchist views in quantum physics. Paul Feyerabend was a proponent of pluralism. Yeah, that stuff's not so cool. All right, this is now about political anarchy. I care about physical anarchy. Anarchy in neutrino physics. The neutrino sector of a seesaw extended standard model is investigated under the anarchy hypothesis. I don't know what this is about, but I'll read it. If it's not too many pages. Yeah, 23. Sounds reasonable. All right, that's, I think, all I can handle right now of cosmology. And that was super cool. I learned a lot. I guess if I'm going to do this, let's open up a picture of the universe. All right, this one. This one we'll have to do. All right. So that was cool. I learned about Casper. Thank you so much for being on chat and telling me about what's up with the physics. I think that without that, I would have had not nearly as much of my bearings as I had, which was already relatively minimal, even with your great help. But I feel like I got a pretty good sense of what people who do cosmology think about and care about from a kind of computational perspective. And so I'm going to go and read a bit about cosmology, now having a little bit of a grounding of when people describe the various equations. Like when you're looking at a new field, even if you have like a reasonable technical background, it can be hard to figure out what's important and what's kind of just noise. Or if you're reading a paper, the paper will often assume a bunch of background. And so like the stuff that they spend the most time talking about are the novel features of the paper, which are often the things that are like most forgotten through time as opposed to the most important stuff. So I think it's often helpful to look at a software implementation. It kind of tells you like people have put a lot of time like modeling these things. These things are probably on the important side, and they kind of draw your attention as you're reading the material. So I'll go do that, and I'll contemplate the universe for a bit. And I'll see you guys next week. Thanks for watching.